Good afternoon, everyone. Welcome to Science Sundays. Science Sundays is a series of lectures throughout the academic year in which we bring in speakers from OSU and across the world who are experts in various topics that are of interest and touch on our lives, and who are also chosen for their ability to present science in a way that's understandable, regardless of whether you have a science background or not. My name is Chris Hamill. I'm in the Department of Physics. I'm also on the Science Sundays committee because I'm the director of a center, the Center for Emergent Materials. We are a group of people that are pursuing the combination of quantum mechanics and complex interactions in nanoscale structures. This leads to a lot of fascinating science, which you will have some chances to hear about, I hope, in this series. But it also can have an impact on our ability to do computation, to process information, and to do it in an energy efficient way, and even to generate energy. Now, neutrinos are not an emergent material, but our speaker today is talking about neutrinos. Our speaker is John Beacom. John is a professor of physics and astronomy. He is also a very, very popular teacher. He's somewhat famous for his excellent teaching and for the how well liked he is by his students. And I think that that's part of the reason that he's able to give a lecture like this so fluently. John is a leader in neutrino observation. It turns out that John Beacom and I came to OSU at about the same time, about 15 or 16 years ago. And at that time, I was struck because John had it, even as a young professor, had the goal of revolutionizing the field of neutrino astronomy. And that's what you're going to hear about today. So thank you very much, John.
Now, I could give a talk about this Science Sundays PDF, but it might be better to switch the screen. There we go. Good afternoon. Thanks for coming. It has long been imagined that we are surrounded by near invisible spirits, that these spirits, if we could only listen to them, would carry important messages, and that these messages would inform us about the universe and its amazing contents, as well as our place in it. On the left, you see a picture of the sun as imagined by Dante about 700 years ago, and illustrated later by Dore. On the right, you see an actual image of the sun as imaged with neutrinos by the Super Kamiokande experiment. It's stunning that both of them have a similar appearance. The reasons are very different, but in both cases, the fundamental idea was that these are the near invisible messengers can tell us about things like how the sun works. And that's what we're going to talk about today. So here's my title. You've seen it. That's what made you show up. Now, there's 3 parts to the title. I broke it up. The first part is astronomy, which everybody's familiar with. And I'm confident that in the question period, nobody will ask me something like, so I'm a Libra, and my boyfriend's a Capricorn, so what should I do? You would be surprised how often I get questions like that on airplanes. A lot. So I know you know what astronomy is, so let's start with that as a foundation. Everybody likes astronomy. And I know that you've heard about neutrinos, and I'll tell you more about them. They are near invisible, but not completely invisible particles. And we can use them to see things in the universe that we cannot see with light. Now, this last part sounds kind of challenging, the made easy part, and that's what I'm going to work on. Now, has anybody ever watched like a magnificent play in a basketball game, maybe with a slam dunk or something, and thought, I appreciate seeing that. Maybe I can't do that, but I can appreciate it and understand it. That's what we're going for today. Okay? So at the end of this talk, it'd be great if you could do neutrino astronomy, and maybe you will. But at the very least, you can appreciate what we're up to. Now, let's start with the neutrinos. Has anybody ever seen a neutrino? No? Nobody here? Okay. So neutrinos, like lots of other things in the universe, we believe they exist even though they're hard to see. There are lots of things we know exist even though we can't see them. Wi-Fi, Everybody believes in Wi-Fi, right? Can't see it. Germs, some people see them, but most of the time they're not real. You can't really see them. Leprechauns, other things like that we know are real, but you just can't see them. Neutrinos fall into that category. So the story of neutrinos is sort of a weird one. And I'm going to begin with telling you a little bit, instead of talking about neutrinos directly, I want to talk a little bit about physics and astronomy. Now, I'd like to ask you to raise your hand if you ever took an introductory physics or astronomy course. Now, keep your hand, let's raise it again, if you loved that course. I see a lot of hands, but not quite as many. So for those who didn't put their hand up the second time, this is what I'm going to call a trigger warning. I'm about to show you some very disturbing images. It's going to give you some flashbacks. It's going to be calm. There's no exam. You'll be all right. Are you ready? The inclined plane. The seasons. Now, when you took introductory physics and astronomy, these are probably some of the things that were emphasized. They are important, but they sure aren't everything, and they aren't why we do what we do. So it's a mistake in those introductory classes to make it seem like the most interesting thing in physics or astronomy are these things right here. It's part of the story, but that's not why we do what we do. And if we want to make it more interesting to you, we ought to tell you what we actually do. That's what I'm going to do today. So one of the things we're trying to find out in physics, among many other things, is what are the smallest things in the universe? Smaller than anything. And then maybe smaller than that. And what laws govern them? And if we can understand those smallest things, maybe we can understand a lot of bigger things. That's a central idea of physics. It's not the only driving idea in physics, but it's a big one. In astronomy, one of the big ideas is what are the largest things in the universe? Larger than you can imagine, much larger than you can imagine. The biggest things, and how do they work? This is what we're trying to do. Does this sound more interesting than the inclined plane and the seasons? And this is something that, a child or someone keeping the curiosity of a child can understand. What's smaller than small and what's bigger than big? The amazing thing is that those two questions are linked. And this is something we've figured out over the past few decades, is that the behavior of the largest things in the universe is very closely connected to the smallest things in the universe. And that's an astounding fact, that these things are not separate directions, but they're really tightly connected. And neutrinos are part of that story. That's more interesting than the inclined plane for sure. Okay, so let's start with the smallest things. If you take a block of wood or metal or whatever and start breaking it up, you start with chunks and then sawdust and then smaller pieces and dust. And you keep on going, and everybody here knows that eventually you get to the level of atoms. And then you know that you can take those apart. There's a nucleus, and it's surrounded by electrons. You can remove the electrons and just look at the nucleus. And then everybody knows you can take that apart into protons and neutrons. And at atom smashers, like the one at Fermilab or the Large Hadron Collider at CERN, we can take apart those protons and neutrons into quarks. Our best efforts to take apart the quarks have not succeeded. As far as we can tell, the quarks are actually point-like. They don't have a size. They don't have any pieces inside of them. That's amazing. So what that would mean is the whole universe is made of Legos, so to speak, of quarks and other things like that, and there is a smallest Lego. There is no smaller piece than a quark, or, we think, an electron. That's amazing. And the way we find those things is, like I said, colliders. We can break things apart into smaller and smaller pieces, but another amazing thing happens at colliders, and that's that we find that new particles that we never saw are created. So ordinary stuff, like this podium here, is made of protons, neutrons, and electrons. You all know that. But there exist lots and lots of other particles that are similar to protons, neutrons, and electrons, but they're extremely short-lived. We can make them very briefly at colliders, and then they disappear. And after many decades of research, we have what we call, this is sort of like the periodic table, so to speak, of the elementary particles. There's only one particle here that's super familiar to you. It's the one in the bottom. That's the electron. Everybody knows the electron. You rub a balloon on your head, you get static electricity, motion of electrons. So, just with a birthday party trick, you can get one piece of this puzzle. The rest take an accelerator. Now, the electron has some slightly heavier, unstable cousins called the muon and the tauon. They're a lot like electrons, but they're heavier and they very quickly decay. They're written on the bottom row. Now, the U and the D there are the up and down type quarks that make up protons and neutrons and everything else we know. So all of the matter, like this podium or anything, all of us, is made up of just those three things. Up quarks, down quarks, and electrons. You can make everything. There's one other particle you're familiar with, and that is written there with a gamma signal on the right-hand side. That's a photon, an individual particle of light. It's not part of matter, but it's part of everyday experience. Now, what about the neutrinos, which are on the second row from the bottom there? So the neutrinos are something weird. They're not in a block of wood, but they're all around us all the time. So why aren't they part of matter? Well, they interact too feebly, too weakly, to be part of ordinary stuff. But they are in the universe in abundance, and it's a mystery why. But we can use them to understand things in the universe. So all of these particles are very, very small. People often say, oh, neutrinos don't interact because they're so small. Well, actually, all of these particles are incredibly small. An electron, like I said, has no size. What makes a neutrino not interact very much is it has no charge. An electron has charge, a neutrino doesn't. So and a neutrino is also small in mass, but that's not the same as not interacting. The not interacting comes from not having a charge. A photon of light doesn't have a mass, and photons interact perfectly well. That's how you can see me. So these smallest things don't include neutrinos. Sorry, the smallest things do include neutrinos, but they're not part of ordinary matter. The largest things in the universe, we started with our solar system, and it's been known for thousands of years that the sun is not alone in the solar system. The planets are there too. And we now know that our sun is but one of many. In the Milky Way, about 10 to the 11 stars gathered in sort of an island. And then this island is surrounded by other islands of stars. It's something like, if the Milky Way is this big, then the next galaxy is maybe this big and about that far away. And that these galaxies just go on and on and on and on. Many, 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 many galaxies throughout the universe. This is all really amazing and beautiful. And if we understand the physics behind it, it becomes even more so. So what does neutrinos have to do with this? Well, the neutrinos are not visible in this picture, but they're everywhere in that picture. And throughout this talk, I'll illustrate how that is. So all of the stars in those galaxies are making neutrinos. When the stars explode, they make more. Some of those stars are able to accelerate particles to extremely high energies, which leads to the production of neutrinos. And in between the galaxies are neutrinos left over from the Big Bang. So if you hold up your hand like this and imagine you're holding something in your hand, like, I don't know, a grape, then you have thousands and thousands of neutrinos left over from the Big Bang inside of your hand. So what we want to do is use these smallest particles to illustrate how the biggest things in the universe work. And neutrinos were witnesses to how all of those things were created. So all we have to do is detect them, and then we'll understand all of that beauty. Okay, so what are they? In more detail. Neutrinos began as a concept. It was observed that a certain kind of nuclear decay, when it happened, there would be a nucleus sitting there minding its own business, and all of a sudden two particles would shoot out to the side. Nothing would go the other way. So what if I were standing here on the stage? I think I'm standing here at rest, and all of a sudden something shoved me in one direction. What would you say? If you saw me move suddenly in one direction, what would you say? Well, you could say, I jumped. Okay, let's assume I didn't jump. Or I was pushed. And you would say, something pushed him, because we know that things that are at rest don't just suddenly move randomly. Similarly, if something breaks into pieces, all the pieces don't go off to one side. If you take a water balloon and drop it, what kind of a mark do you get on the floor? A round one, right? So if you saw a hemispherical mark on the floor because all the water went in one direction, you would think that that was really weird. And it's exactly what happened in this nucleus, and it's really weird. The nucleus is sitting there, it decays, everything goes out to one side, and so people said, that doesn't make any sense. There must have been more involved. And what was involved was, people said, there's a something that carries away momentum and energy in the other direction. Even though you can't see it, something is going there. And that something was called a neutrino. And the author of this idea said, I have done a terrible thing. I have postulated a particle that cannot be detected. So basically, someone was sitting there and all of a sudden they got shoved. And he said, well, something did that. So all he did was put a name on something. He had no explanation for what something was. Now, if you think about it, that's kind of a cheap excuse, right? It just says, something happened, I have no idea what it is. It's sort of like the dog ate my homework. So there are a lot of other unsolved problems in physics, and if you're crafty, you start realizing that you don't have solutions to all of the kinds of things like this. But if you're crafty, you realize you could solve all of them. All you have to do is say the magic word, neutrinos. Because nobody can find out if you were right or wrong. Any one of those problems, oh yeah, it's neutrinos. It's a perfect liar's license to blame anything you want on neutrinos and nobody will ever be the wiser. And the only reason this works is because neutrinos can never be detected. What if that were to change? So we saw that this thing happens, and also it's seen that this thing happens. And the idea is, could this thing happen? And what this thing is if there are decays that produce neutrinos, maybe if you run the neutrinos in, they'll interact with matter and make the decays go backwards. That's so-called neutrino capture. And people realized that this had to exist at some level, and all the liars who were saying, oh, we'll blame neutrinos for all of our problems, got very, very nervous. And then, importantly, there was a calculation by Bethe and Peierls, and they said, don't worry, we calculated this, and even though neutrinos must interact in principle, it'll never be detected. So all of the lies were safe. Anything you want to blame on neutrinos, in principle, you could be caught, but it was never going to happen because neutrinos can go through a light year of lead, we'll never catch them. Now, these predictions were made by theorists, and not everybody listens to theorists, in particular experimentalists. And so people tried to detect them anyway, just like people try to detect leprechauns. So the first thing you need is a prodigious source of neutrinos and a friendly operator to help you out. And a prodigious source of neutrinos is a nuclear reactor. Why? A nuclear reactor, nuclei are being split or fused, or, well, in the reactors we have, nuclei are being split, which means we're changing one chemical element into another. And whenever one chemical element is changed into another, neutrinos are produced. So, in principle, what you should be able to do is put a detector right next to a nuclear reactor. Now, you may have heard in the radio advertisement for this talk, I mentioned that the original idea was, for detecting neutrinos, was let's just set off an atomic bomb and put a neutrino detector nearby. And construction had started on this project before someone said, maybe that's not the greatest idea. Maybe what we should do is put the detector next to a nuclear reactor. And so they did. This is a picture from the 1950s when they began constructing that experiment. It was called Project Poltergeist. It preceded the movie of the same name, a Poltergeist movie. And in 1956, they detected neutrinos. They weren't supposed to be able to. So now, the bottom just fell out on the neutrino theorist market because all those things the neutrino theorists had said, probably neutrinos are involved. Now we have to make sure that all of those explanations are consistent because neutrinos are actually detectable. That makes my job harder. It also makes it more interesting. Soon after neutrinos were found to be detectable, somebody said, well, maybe we could do astronomy with them. It turns out that whenever conditions in an astrophysical system are hot and dense, or wherever you're changing one chemical element to another, or wherever nature is constructing particle accelerators, neutrinos are born. And if that sounds like Tom Joad's speech in The Grapes of Wrath, that's deliberate. Now, the cool thing about these neutrinos is because they pass through almost everything, it enables us to do astronomy in a different way. And as I'll illustrate in a few minutes. It enables us to see the inside of a source instead of the outside. It enables us to see the original energies of the reactions deep in the core of an object instead of how they look once they eventually emerge, and so on. The only problem is it's hard. But this problem is solvable with better and better detectors. So how do you make a neutrino observatory? The first thing you need is a lot of material because neutrinos don't like to interact. So right now, neutrinos are streaming through all of us. And right now, the number of neutrinos going through your eyes is about 10 to the 12 neutrinos per second. And it's important for you to realize it's totally harmless, okay? it's important for you to realize it doesn't matter which way you're facing or where the sun is. The neutrinos are either going in this way or they're coming out of your eyes, sort of like in a superhero comic book, which is pretty cool, but they're also coming out of your elbow in equal numbers, so it's not really special. So those neutrinos take a lot of material to stop them. Very rarely is that possible. So one way to do this is get a giant pile of material, and then occasionally, out of nowhere, an invisible particle will come in, strike something like an electron, and it'll shoot off. And when it shoots off, it'll make a little flash of light. And we can detect that light with very sensitive light detectors. So where can you get this much material? So you need something that's very, very big, but it also needs to be transparent to light. And an example is the Super Kamiokande detector in Japan. This is about 40 meters high, about 40 meters wide. So a cubic meter of water, or a cubic yard, whatever, it's something like this. Yes, that's a lot of water. It's a ton of water, literally. This has 50,000 of those cubic meters of water in it. And it's surrounded by very, very sensitive light detectors. This picture doesn't do it justice because it doesn't set the scale. See the people in the boat? Barely? So there are about 10,000 light sensors on the wall. Those are called phototubes. Phototube works basically like a light bulb in reverse. Light bulb, you put in electricity, out comes light. A phototube, a little bit of light comes in and a little electrical signal comes out the base, and we can read that out. That tiny, tiny boat shows you how big this detector really is. And it's so sensitive that just a few photons of light produced anywhere in it can reach the detectors and be seen. Anybody ever been scuba diving? A bunch of people? What would you say about underwater visibility of, say, 10 meters? Pretty good? 20 meters? Nice. Super Kamiokande, the water is transparent to 70 meters. It's the cleanest, purest water on Earth. So where would you put these observatories? Well, we have to put them where there aren't other signals, like, for example, from cosmic rays. We're all being bombarded by cosmic radiation from space right now. Don't worry, it's mostly harmless. But if we put the detectors deep underground, we can avoid that. I'm going to show you some pictures of a trip I took, not to the Super K detector, but to a different detector. It's in a secure, undisclosed location. But I'll show you what it looks like underground. So this is the approach to the detector. It looks, this tunnel could have been built, hundreds of years ago. It's a dirty, wet, horrible place. That's me there in the backpack, deep under a mountain in a remote location. At the end of this, basically you walk through this long sewer, and then remember in Jurassic Park, when you drive through the tunnel and you pull up at a door that looks just like this? Including in the white vans or whatever. So we pull up here, and then in the middle of this sewer is this 21st century laboratory. And this is the beginnings of a new neutrino observatory. And this shows you, gives you a feel for what it's like to build these things. They're all situated underground to shield them from cosmic radiation. And it has to be because neutrinos are so rarely interacting that we have to make sure that nothing else tricks us into thinking it was a neutrino. Okay, let's move on to the sun itself. So in my Astronomy 101 class, okay, I'll warn you, this is going to be a trick question. I usually ask people, why does the sun shine? And like 18 hands go up immediately and say, nuclear fusion reactions. That's sort of right, but it's sort of not. Why does the sun shine? Now that I told you that that's not the answer. It's hot? Excellent. The sun shines because it's hot. It keeps shining and it stays hot because of nuclear fusion reactions. But if you turned off the nuclear fusion reactions, the sun would still be hot. It just would take a long time to cool down. And just by looking at the outside of it, we can't tell if it's hot and somebody left it alone or if somebody's keeping it hot. So everything shines because it's hot. So this cup of coffee is shining. Okay, you see light on it, right? That's just reflected optical light from the room lights. But if you had infrared eyes, you would see that this is emitting infrared light because it has some warmth. And everything is emitting some kind of electromagnetic radiation because it's not at absolute zero. Now the question is, what keeps it hot? And the question is the sun being kept hot, or is it just hot and it's cooling down? And that goes to the question of how old it is. So let's find out. Here are the observed facts of the sun. So an ordinary incandescent light bulb, maybe some of you have seen those, they used to exist. An ordinary incandescent light bulb is 100 watts. The sun is about 10 to the 26 watts. So it's incredibly luminous and it's very, very hot on the outside. One of the interesting ways we can find out what the temperature of the sun is, we can't go there and stick in a thermometer. One thing you can do though is you can heat up a piece of metal until it's the same color as the sun, and then you can measure the temperature of the piece of metal and figure out the temperature of the sun. Because everything at the same temperature glows in the same color. Now, this doesn't tell us how old the sun is, it's just there. Now, these two fellows, so by the way, these pictures are obviously really old, but has anybody been to the short north recently? Have you seen younger versions of these hipsters walking around? Especially the guy with the diagonal beard. I mean, that's pretty styling. So, these two people had a serious disagreement about how old the sun is. And does anybody recognize these people? Oh, wow. So Darwin and Kelvin, excellent. So Kelvin said the sun must be young because otherwise it couldn't be so bright. Otherwise it would have cooled off. Kelvin thought the sun was bright because, a bunch of material fell together, smashed together, heated up, and is gradually cooling off, right? So if you drop a hammer from an Empire State Building onto the floor, it heats up, right? In a similar way, all of this material, don't actually drop, just because there's going to be a video of this, so let me say, please don't try that at home or at the Empire State Building. Don't actually drop a hammer. Okay. Anyway, if you did, then it would heat up the ground a little bit, and when all this gas came together, by falling together, it heats up. And Kelvin said, well, that's why the sun is hot, and I think it can stay hot for about 100 million years. And Darwin said, well, you may be right, but I think the Earth and the sun must be much older than that to give time for the evolution of species. At the time, both of these theories were under serious debate. So Kelvin thought that the sun and the Earth were not very old, maybe 100 million years. Darwin said it has to be much, much older. How can we find out? So probably some of you have children, and maybe you've encountered the following situation. In the closet or behind the couch or something like that, you find all of their lunch boxes that they brought home from school. And they're full. They have stuff in them, right? So there's like 8 lunch boxes under the couch, and they all have some kind of food left in them. And you're trying to figure out how old they are because the ones that are super old, you're not even going to open them. They're just going straight to the garbage. The other ones that are not too bad, you might, be able to dump them out and start over. When you pick up this kid's lunchbox and you want to know how long has that been sitting there, maybe there's a way you could find out. If you ask the kid, you know what the answer is, right? I don't know. I've never seen that lunchbox before. So let's see if we can figure out a way to measure how long that lunchbox has been sitting there. So let's go back in time and let's pack a good, nutritious lunch for our kids. We'll start with a banana, maybe some rice, Hostess, maybe not so nutritious, but whatever. And then also a piece of uranium. Just to see if they're paying attention. Now later, this is what their lunchbox looked like when you packed it, and this is what it looks like when you found it under the couch. And what we want to know is, how long has that been sitting there? So how are we going to do that? Well, we're going to open it up, we're going to be brave and open this thing up and look at it, and how are you going to tell how long it's been sitting there? Did I give you a clue? Decay. So if you open it up and the banana is still yellow and looks decent, it hasn't been there that long. If the banana is a shriveled, gooey mass, but the rice looks halfway decent, maybe like a week. If even the rice is gnarly, okay, and then by the time that the Hostess Twinkies are gnarly, just straight to the garbage with the tongs. And in a similar way, we can figure out how old the Earth and the sun are by looking at decay, not of Twinkies, but of different radioactive isotopes. So some isotopes of uranium and thorium live for billions of years, and other things live for less time. And by looking at how much of those isotopes exist in the Earth and the sun, we can figure out how old they are. That's an incredible idea. And it works And the answer is 4.6 billion years old. So that means that the sun must be shining for about 4.5 billion years. But Kelvin said, if we don't keep warming it up, it'll just cool off in 100 million years, much less time. So something has to keep it hot. What is that? Well, let's start with something we know. Now, if I weighed all the players and added them up, you know that this would be equal. I know that the coach would say, the sum of the team is more than the sum of the individual players. Yeah, okay, whatever. But if we added up the players' masses, it would just be conservation of mass. How many players? Add them up, that's the total mass of the team. Now, let's think about what happens with nuclei. Somebody want to guess on this one? Is this equals, less than, or greater than? So a helium nucleus is made up of 2 protons and 2 neutrons. And I have 2 protons and 2 neutrons separately. The parts or the assembled thing? Which one has a greater mass? Well, so I heard a couple of good answers, and the correct answer is the parts actually weigh more. So when you put them together, it ends up weighing less. Now, one way to think about that is if you had a helium nucleus and you wanted to take it apart, it requires that you put in energy. You have to go there with a hammer and chisel or something, or an accelerator and break it apart. And by putting in energy to take it apart, that means when you put it together, it releases energy. Just like when I drop this, it'll release energy in the form of sound and vibrations. Because it became a little bit more gravitationally bound to the Earth. Not very much bound, but in a nucleus it's a big effect, and it's about 1% of the mass is lost. 1% is a lot. So, many of us are tracking our weight to 1%. And if, one day, you eat some protons and neutrons and your mass changes by 1%, that's a big deal. So this was figured out in the laboratory, that a helium nucleus has less mass than its parts. And then Eddington said, maybe that has something to do with this newfangled E equals mc squared thing, and maybe that explains where the energy in the sun comes from. And he was right. The energy that started as mass ended up as released energy in the form of light and kinetic energy. So the idea was, if you put 4 protons together, you would turn 2 of the protons into 2 neutrons, and then out would come 2 anti-electrons and 2 neutrinos plus some energy. And it's the E equals mc squared difference that gives the energy of those particles. And if this theory were right, then what would happen is, every time a nuclear reaction occurs in the core, a neutrino would come out immediately, like that. And every time a nuclear reaction happened in the core, it would heat the sun from the center, and gradually that heat would go to the surface and would come out as visible light. So in other words, if we turned off the reactor right this minute, the neutrinos would stop instantly, but the sun would stay hot for about 100 million years. So if you see the neutrinos, it tells you that the core is turned on right now. If you see the photons, it tells you that the core was turned on 100 million years ago. If only we could measure those neutrinos. So this is what we see. This is that image I showed you at the very beginning. This is an image of our actual sun as imaged by neutrinos that have scattered electrons. That little blob in the middle is a little bit of an overestimate on how big the sun actually is. So it's a little confusing that the sun in neutrinos appears to be bigger than the actual sun. And in fact, the neutrinos are coming from a tiny part of the core. And the reason for this is the neutrino detectors have blurry vision. When you scatter the electrons, they tend to blur. It's clear that we're seeing the sun, it's just a little messed up. So those neutrinos are not coming from outside the sun, but actually from inside it. This is an incredible feat. One small problem was we only measured about a third as many neutrinos as expected. And when that happened, people said, well, maybe the theorists don't know how to calculate anything. Stephen Hawking said, maybe there's a black hole in the center of the sun that's gobbling up matter and heating the sun that way, as opposed to nuclear fusion. All kinds of other ideas came about, and none of them could explain why we saw fewer neutrinos than expected. But then people had the idea that if you started with 3 electron-type neutrinos, which is what the sun makes, that as they traveled, they could turn into different types of neutrinos. You may remember on that periodic table of the elementary particles, there were three kinds of neutrinos. There was electron neutrino, muon neutrino, and tau neutrino. And if this were true, then we should be able to measure this. So some of you probably heard the recent Physics Smith lecture by Art McDonald about the 2015 Nobel Prize in Physics. And that's what that experiment did. They found that the electron neutrinos, about 1/3 as many as expected, were detected, and the other flavors made up the other 2/3. And if you add all of these together, the sun was producing exactly as many neutrinos as expected. So what that meant is, not only we understood the nuclear fusion reactions in the core, we also understood and learned something about the properties of neutrinos. Something that's quite astounding. And if we put all of that together, we now have a new understanding of the interior of the sun. So we now know that the sun is hot on the outside because it's being kept hot by nuclear fusion reactions in the core. We are able to calculate those reactions very, very precisely. And from the measured flux of neutrinos from the sun, we're able to figure out the temperature in the core to about 1% precision. Pretty astounding. That temperature is 15.7 million degrees. It's extremely hot, but we're able to measure it very well because of the neutrinos. That's an astounding feat because when you look at the sun with your eyes, anybody ever actually done that? Okay, who was told not to look at the sun? Everybody? Who actually did it? Yeah, okay, everybody. If you look at the sun with the outside, you're only seeing, if you look at the sun with your eyes, you're only seeing the outside of it. With neutrinos, we're actually seeing into the core. It's incredible. This is the beginning of making neutrino astronomy a real science. Now, how do we do that? Well, we go looking for other things. And one of the things we look for is exploding stars called supernovae. And if you'd like to learn more about this, the recent Science Sundays lecture by my colleague Todd Thompson talked about supernovae, and that lecture is now available on YouTube. I'll give you the address, the URL at the end. One of the things we looked for was exploding stars. So where should you look for exploding stars? I always look where there's a giant arrow. And it's very effective. And then here's what happened next in optical. And an enormous burst of neutrinos, light and neutrinos happen at about the same time. Now, in optical light, the supernova is nearly as bright as a whole galaxy. If you had neutrino eyes, like Geordi LaForge in Star Trek, then it would have been 10 to the 15 times brighter in neutrinos than the rest of the galaxy. So that's cool, and we learned a lot about that. We learned how supernovae actually work. We learned that basically the way they work, a massive star collapses and makes a nucleus as massive as the sun. That's pretty incredible. We also learned some things about the neutrinos. But instead of dwelling on this, I want to tell you about one of the most recent discoveries. So there's a detector called IceCube at the South Pole. It's about a cubic kilometer in size, really, really enormous. And it's instrumented with these light detectors called phototubes. And it's very, very dark under the ice. And occasionally when a neutrino interacts, it'll scatter some particles that do interact, like protons, electrons, and other things. And those will make flashes of light. And those flashes of light can be found caught in those phototubes. Now to get there, you have to go to the South Pole. So this is the business class section of the C-130 jet that carries you to the South Pole with all of your gear. And then when you get there, you get to see amazing things like the Aurora Australis, if I pronounce that right. And that's caused by cosmic rays from space hitting Earth's atmosphere. So that's part of the reason IceCube is underground, is to get under ice, is to get away from those cosmic rays. The construction is an enormous feat. It requires digging holes that are about this big around and about 2.5 kilometers long. Now the picture in the bottom left there was the last photo taken by a graduate student who messed up something on the experiment. They were told to go ahead and message that back, and then they would be pulled back up. That's all that happened there. Just kidding. Presumably they put a camera down there. This is quite an engineering feat to drill these holes. They're drilled with hot water. Now, once they're drilled and they put in all the phototubes, they waited for something to happen, and this is what happened. Some particle, a very high energy neutrino, came in through the part of Earth, through the ice, into the detector. It's happening all the time. The neutrinos are going through and nothing's happening. But some of these neutrinos interacted. This neutrino hit a proton or a neutron. It made a very high energy proton or neutron that made many more, and it made a bunch of other subatomic particles, and these all made a giant flash of light. Now, by our optical standards of our eyes, it was not that bright, but in the detector, which is extraordinarily sensitive to light, it was very bright. So this energy of this neutrino was very high. So these photons that you're seeing bouncing off my face right now, these have an energy of about 1 electron volt, the photons. This particle, a single neutrino, had an energy that was 10 to the 15 times higher. So more or less, when it smashed into the detector, it made a giant flash of many, many, many photons, and those were what was detected. The size of this light flash in the detector is a few hundred meters across. So it was very, very bright. Now, since then, many more events have been discovered, and we're trying to figure out where they're from. And the interesting thing is we don't know. With the sun, we had kind of a neat, tidy story with a well-developed theory and great experiments, and it all came together. Same with supernova 1987A. With this, it's basically just pure discovery. We've built the detector. We've seen neutrinos from outer space. We don't yet know what's making them. And that's what's great. We get to find out. We do know that these neutrinos have very high energies, as I just remarked. So the Large Hadron Collider at CERN, which is the result of thousands and thousands of people working over a few decades, is able to accelerate particles to about 10 to the 13 electron volts. So somewhere in nature, just produced by happenstance, is some kind of accelerator that not only can produce much higher energy particles, but incredibly brighter than CERN. If you go to CERN and the beam is turned on, and you were foolish enough to walk through the beam, that would be toast for you. It would be really bad. That's why they don't allow anybody in the tunnel when the beam is on. This beam of neutrinos from somewhere halfway across the universe is so bright that we can detect it from there. So it's incredibly more luminous than whatever is being built at the Large Hadron Collider. And nature assembled this seemingly by happenstance. So what I'm trying to do is make neutrino astronomy real. First time I bring up neutrino astronomy to anybody, they say, that doesn't sound real. Astronomy, that's real. Neutrinos, not real. So what I mean by real is we've detected a few different kinds of sources, but to make it really a bigger field, we want to detect many, many kinds of sources across a wide range of energies, and then synthesize all of that knowledge to make it make sense. We're working with my students and postdocs and other colleagues on a wide variety of things. I won't go into the details. We're trying to better understand how detectors work so we can get more out of them and to better extract information from the handfuls of neutrinos we do observe. So I think it's obvious why this is exciting to me. So let's recap a little bit why it might be exciting to you. Here's the part that's exciting to me, is we get to use X-ray vision, so to speak, to see into the core of the sun, the center of a supernova, extremely powerful accelerators all the way across the universe. It's obvious that that would be fun for a neutrino astronomer. What makes it fun for you? Maybe that sounded pretty cool. Don't get me wrong. But what makes it fun for you is the understanding that we get from that. So following scientific curiosity is a natural and ennobling human activity, much like pursuits of other things in the humanities and the arts. And together, all of these things enrich and enlarge our whole human experience and our understanding of our place in the universe. And that's deeply important and deeply profound, even if nothing practical comes of it. But you might say, well, I'm only interested in this if something practical comes of it. Okay, we have that too. So this is a picture of a nuclear reactor. Now, imagine that you tell me that you have a nuclear reactor, and I'm not sure if I believe you or not, and it's in a sealed building and you won't let me go in, but I am allowed to build a detector next door. If I'm allowed to build a neutrino detector next door, and your reactor is on, I'm going to get neutrinos. If your reactor is off, I don't get neutrinos. You cannot hide them from me. no matter what you do. So the people who build these neutrino detectors for neutrino astrophysics are also capable of building neutrino detectors for other purposes that may have some practical value. Furthermore, all the experiments we do in physics and astrophysics, we're building the most sensitive detectors ever constructed by humans to tackle some of the most difficult problems. And we're training our people, our graduate students and postdocs and undergrads, on how to think about those things, how to create detectors like that, and how to operate them. That training makes them great for doing all kinds of things in any area of science, and many of them carry those skills to other areas like industry and so on. And just like research in biology is the nourishment for the tree of medicine, research in physics is the nourishment for the tree of technology. And our lives are increasingly technological. And having people who understand and can develop that technology is crucial to the success of our society and the fate of all of humanity. That's why we do what we do. So to wrap up, I want to show you a little bit about more what we do on a day-to-day basis. So as Chris mentioned, I'm the director of the Center for Cosmology and Astroparticle Physics. It's a joint effort of the physics and astronomy departments here. Here's a picture of what some of our space looks like. This is in the physics research building. That's us gathering there on that second bridge. Zooming in a little bit, this thing here is a photomultiplier tube that I showed you earlier. This is an actual one. It's about this big around. This is hand-blown glass by a master craftsman. There's only a handful of people in the world who can make these things. And these are some of the other basically scientific art kind of things we have around in our area that are fun to look at. My colleagues are also constructing new detectors. This is a picture of a special kind of radio antenna that's being used to detect ultra-high energy neutrinos, also at the South Pole, not in IceCube, but in a different experiment, by my colleagues Amy Connolly and Jim Beatty. And how we actually do our work on a day-to-day basis involves a lot of discussion, and that involves training the next generation of scientists, the postdocs, graduate students, and students, on how we do these really, really hard problems, how we solve these really, really hard problems. It involves a lot of talking, it involves a lot of chalkboard work, and then, a lot of work deriving equations and writing computer programs. But a lot of it is just based on talking about ideas and trying to figure out the sharpest point we can make. We're also working on educating the next generation of scientists, for example, through the Science Sundays series here, to help interest kids and other lifelong learners in what we're doing to inspire future generations. Now, to wrap up, anybody, I think, can appreciate the beauty in this photograph of one of the Hubble Deep Fields. And now that you know some things about astronomy, I think you can appreciate it more because you can see some stars, some galaxies full of stars themselves, the depth of space. It's really amazing what you can see in this if you understand some astronomy. If you understand some physics behind it, it's even more beautiful to imagine how all of these things work. These stars are processing nuclear elements in their core through fusion reactions. Those fusion reactions generate energy for the stars. They make neutrinos that we can detect. And they also create all of the elements necessary for life. So the existence of life in the universe comes from elements that are made in stars. So all of the iron and calcium and stuff in us, that was made in stars and supernovae. And neutrinos are a witness to the creation of those elements. And of course, sunlight is necessary for powering life on Earth. Each of those galaxies has something like 10 to the 11 stars. Something like 10 to the 11 galaxies. That's like 10 to the 22 stars. We now know that it is common to have planets around stars. And so that opens up the idea that maybe life in the universe is not rare, not here only on Earth, but maybe is ubiquitous. And it's amazing to think the neutrinos are sort of there everywhere, bearing witness to how all of those conditions were created, and maybe somebody else is helping to see those neutrinos too. Putting it all together, the smallest particles in the universe are helping us understand the grandest reaches of the cosmos itself. And everywhere we look, as John Muir said, when we try to pick out anything by itself, we find it hitched to everything else in the universe. The largest and the smallest things together. Neutrinos play a crucial role in that. Thank you.
John, thank you for a great talk. That was wonderful. We have some time for questions, but before we start those, I'd like to remind everybody that there will be a reception following the talk.
In the traditions room.
It's in the traditions room. You go upstairs, I think there will be signs. So if you don't have a chance or you don't think of your question in time, you can go up to the reception and you'll have more of an opportunity. All right. Do we have any questions?
Start with kids.
Yes, we start with the kids. So I don't know if you count or not. Let me see. Well, okay. We'll start there.
Go ahead, sir. Yes. Okay, so what this gentleman asked is what kinds of energies do we detect? As I remarked, visible light that we can see with our eyes is about 1 electron volt, very roughly. The neutrinos from the solar core are about between 1 million and 10 million, roughly, electron volts per particle. And the neutrinos seen by IceCube go up to 10 to the 15 electron volts per particle. So it's pretty incredible. Like I said, our eyes were designed to detect optical light, and yet nature is able to make incredibly higher energy particles, and that's an interesting mystery.
Wait, there's two people. So the person in red first, and then the person in gray next.
When you talk about neutrino detectors, if you use, let's say, water and fluids, presumably the way you detect forces of neutrinos make a bigger detector.
Yes.
Are there other technological approaches or other approaches to detection that would allow you to make more progress rather than just making bigger detectors in a big way?
Yeah, a great question. So what this gentleman asked is, one way to detect more neutrinos is to make a, remember in Jaws when he said we're going to need a bigger boat? So that's what we say all the time when we can't do what we need to do in neutrinos. We always need a bigger detector, but there's another way to do it, which is to make the detectors more sensitive. So I mentioned that detectors have signals and backgrounds. So a detector is here, and in comes a neutrino, and it makes a signal. That's great. The problem is if there's anything else in there that looks like a signal that makes the backgrounds, that makes it harder to see. So for example, if there are radioactivities in the detector, then when those radioactivities occur, they can shoot an electron out, and it looks like an electron got hit and scattered by a neutrino. So they go to great lengths to remove all of those radioactive impurities from the detectors. Still some remain. There are other kinds of backgrounds, and that's a key focus of my work. It's sort of illustrated by the two pictures in the middle here of really getting into the nitty-gritty of the nuclear physics of what causes these backgrounds and trying to find ways to isolate something, two things that look like identical, to say, aha, actually that one was a background and that one was a signal. So what I'm trying to do is reduce the size of the haystack so that it's easier to find the needle. Does that answer your question? Okay.
In the particle physicist and quantum mechanics, what forces affect neutrinos that allow us to detect them?
Yes.
Things like magnetism affect them, gravity affect them.
Okay, great question. The question was, wait, you didn't talk about any forces that affect neutrinos, so how could you detect them? Great point. So neutrinos, because they have no charge, basically do not feel electricity or magnetism. Through some quantum loop things, they do at some extraordinarily small level, but don't worry about that. Basically, they don't. Neutrinos have almost no mass, so they barely feel gravity, although when there's so many neutrinos in the universe, their gravitational effect can be a little bit important. But individual neutrinos, the way to detect them is through what's called the weak interactions. And the weak interactions are what turn a neutron into a proton or vice versa. And when that happens, a neutrino was born or died. And those are well, they're called the weak interactions because, well, they're weak. They hardly ever happen, but they're very, very important. Does that answer your question? Okay. Let's see. How about you? Go ahead. Okay, great question. The question was, the sun is constantly emitting neutrinos. What happens if we don't catch them? So first of all, most of those neutrinos go out through the sun, nothing happened. Some of them go through Earth, nothing happened. All the ones that go through the detector, almost nothing happens, but they just keep filling up the universe with more and more neutrinos. And all of the stars in this picture here are also filling up the universe with more and more neutrinos. Now you asked if the neutrinos can decay. In principle, yes, that neutrinos, because they have mass, could decay into a different kind of neutrino with a little bit less mass. We're looking for that effect. I could show a picture of that. And we haven't seen it yet. But we think that basically neutrinos are stable or very long-lived. So they're just kind of filling up the universe. Does that answer your question? Okay. Yes, sir. Oh, I was just joking about that. So why was the location of the detector undisclosed? Okay, so I was just having a little fun with you. That detector, you may want to guess where it is. Well, there's a lot of places. So here's how you get there. You fly to Beijing. Everybody's heard of Beijing. Then you fly to Chengdu, which many people have heard of Chengdu. It's about 5 million people. Then you fly to Xicheng, which most people haven't heard of. That's about 500,000 people. It's a famous place because that's where they launch rockets for the Chinese space program. And then from Xicheng, you get in a convoy of vehicles and drive for an hour or two through a bunch of villages. And then you start driving on roads that even your Chinese hosts say, this is not on my map. Interesting. So hundreds of kilometers of these roads, including hundreds of kilometers through tunnels through the mountains in the western part of China in the Sichuan region. The mountains there are sheer like this. They're incredibly, incredibly steep. And it's not like a mountain like a cone. It's like ridges like that. It's almost impossible to get around. And deep in these tunnels is where this lab is situated. And the reason it's there is they built these tunnels for a giant hydroelectric plant on the Yaolong River. And part of the way the dam works is the river takes a hairpin turn like this. And notice that as the river goes around the mountain, it goes lower down. And so what they do is they run water through a pipe 17 kilometers through the mountain to get to the other side. And then there's a bunch of other pipes just for access, and that's where this is. So it's not actually a secret, I'm just goofing around. Yes, sir?
Does it have wavelength and frequency?
Great question. Question is, does a neutrino have a wavelength and frequency? And the answer is sort of yes and sort of no. So electromagnetic radiation, as you know, has well-defined wavelength and frequency, and their product equals the speed of light, as you know. And, for example, X-rays have a high frequency and a low wavelength, and radio waves are the other way around. Neutrinos, because they're massive particles, are a little bit different. They have a quantum thing called a de Broglie wavelength, and that's incredibly small. Yeah, so that's incredibly small. It basically goes like 1 over their momentum, or h over momentum, yes.
Can you solve for that?
Yes. Yes. So the neutrino wavelength is incredibly small. I could calculate some examples for you after the talk. But it's very, very small because the neutrinos are so high in energy. Let's see. How about, ma'am? Okay, great question. Question is, do neutrinos impact biology? We think no. Probably once in your lifetime, a neutrino will interact somewhere in you, but it's pretty harmless. If there were a nearby supernovae, like really, really, really nearby, then that number could go up, but that would be the least of your problems because, the atmosphere would be on fire and all those other things like that. Right? So we think that they have nothing to do with biology, but it's interesting to wonder. Next question. Sir? Yeah, great question. How can we tell where the neutrino is coming from? We have poor directionality, and then also it's hard to tell how far away it's coming from. And so we have to use some reasoning based on other things like the energy. So for solar neutrinos, we know the energy range. And of course, the sun appears to move across the sky. So if you're seeing neutrinos from there and you're wondering, was that the sun or something else? If you see the neutrinos from here later, it was the sun. And through a wide combination of techniques, we eventually try to piece this together. But don't get me wrong, neutrino astronomy is hard. I said at the beginning I would make it look easy, but it actually is hard. Actually, one thing I meant to say at the beginning was that at the end of the talk, I wanted to leave you with astrophysical neutrinos in your mind. And actually there are. They're passing right through you all the time, but I actually didn't cause that. Yes, sir. Yeah. Yep. Yeah. Great question. So when an electron is struck, it makes a little flash of light in that direction, and it makes a cone of light. And then from the fact that it lights up a circle on that wall over there, and not over here or something, you can tell it's from there. And by carefully reconstructing when and where the phototubes got hit, we can figure out the direction of the neutrino. It's hard, and that's why it's a blurry image. Another question? Yes, sir. Good question. Let's see. So the question was, of all the neutrinos passing through the super chemioconductor detector, what fraction interact? I cannot remember the number right now, but I do know that, so super K is about 40 meters tall and 40 meters wide. And most of the time neutrinos go right through it. If you replaced it by a little square of perfect neutrino detector, so that like everything that hit that square would definitely interact as a neutrino, that square is about 10 microns on a side. So it's incredibly small. So basically what you need is something like 10 microns compared to 40 meters quantity squared. Very small. Yes, sir. Great question. He asked how fast do the neutrinos travel? Because neutrino masses are incredibly small. Didn't really talk about that today, but that's an active area of research. All the neutrinos go at 0.99999 whatever of the speed of light. So the way we can tell apart the energies of the neutrinos is, when a low energy neutrino hits an electron, the electron gets a certain amount of energy. When a high energy neutrino hits an electron, it gets more energy, and we can tell from how much energy it imparts to the detectable particles. Yes, sir, behind you. Yes. We believe that neutrinos may be instrumental. The interactions of neutrinos may be instrumental for making supernovae explode. And I encourage you to watch Todd Thompson, he's sitting right next to you, Todd Thompson's talk. Now, maybe I should wrap up, but I want to end with something important. I know many of you are curious to know more, and so I'll leave this slide up, and you're welcome to take pictures of it now or on your way out. So first, a little bit more about this series. It's been going on for several years, and we've been really gratified to see how interested people are. And if you're not on our email list, I encourage you to sign up. It's through the webpage, or you can talk to Jasmine outside. The emails come about once a month, not a big deal, and they'll also alert you to other things like the Physics Smith lecture and the CCAP Baird lecture. For the past about year, we've been putting videos of our talks on YouTube. It takes us a couple of weeks at most to turn them around, but a bunch of those are posted, and you can find those. We now have a YouTube channel under OSU Arts and Sciences, but just search for Ohio State Science Sundays. And we're interested in growing the potential of what this series could be, and if anybody is interested in talking to us about that, we'd be interested to hear your ideas. And then at the bottom, there's a bunch of other things you could find for further exploration.
All right. Let's thank John again for a great talk.